Good afternoon, class. This is an experiment in giving lectures on YouTube, as was suggested by one of you at our last in-person class. I hope all of you are staying healthy and well. And this isn't a normal lecture, but we can use this as an opportunity to test out whether this is a viable way for me to continue to teach you during the semester. So this is going to be a short, not quite a lecture, but just a note, and we'll go over the midterm. So question one was to take a wave and show how you determine what the wavelength and the velocity are in terms of k and omega. Now, first of all, I want to make clear to everyone, especially after grading the midterms, that this has nothing necessarily to do with electromagnetic theory or quantum mechanics. It's simply the property of waves in general that have this wave function. And so those of you that went to Maxwell's equations or Schrodinger's equation or something like that to try to come up with the answer were along the wrong track. It's simply the fact that it's a wave, and what it means is that if you go a distance z plus lambda, then the phase of the wave has changed by 2 pi. So k times lambda is equal to 2 pi. And so that was the first part of the question. The second part of the question was what is the velocity? And the way I taught you how to do that is that if you plug in z plus delta z and t plus delta t, meaning you've gone a distance delta z and a time delta t, and if the phase then is equal to what it was when you started, then delta z over delta t is the velocity of the wave. So solving from this, if these are equal, then it means that k delta z is equal to omega delta t. I'm sorry, k delta z minus omega delta t is equal to 0. And so k delta z is equal to omega delta t. So delta z over delta t, which is v, is equal to omega over k. So that's the solution to the first problem. Now going on to the second problem. This was testing your understanding of the result of the conic penny model, which in general is that any band structure, the valence band is given by E sub v minus a quadratic, and the conduction band is given by E sub c plus some quadratic. And so I plugged in a couple of coefficients here, and the question is, what is the ratio of the electron effective mass to the hole effective mass? Now, here I could perhaps have written the answer a little bit more, but we'll go with this. Some of you got confused about E sub v and E sub c, and I'd like you to go back and think about this just on a plot basis pictorially, because the answer is very simple. Let's start with E sub c. So for for any conduction band which curves upward, you can write it as the some energy plus something times k squared, meaning it goes up on both sides of the k-axis equally. And all effective mass theory is telling you is that you can rewrite that coefficient as h bar squared k squared over 2m, where m is the effective mass. So, jumping down to the conduction band, since we started with that, what that means is that if you replace this 2c naught here with h bar squared over 2m e star, that tells you what m e star is, because then the energy is going as h bar squared k squared over 2m. And the same thing with c naught. You replace c naught for the valence band with h bar squared over 2m h star, and that tells you what the whole effective mass should be. And so solving for those two things, you get the ratio of the masses is 0.5. Now, perhaps, so the equation, is very simple here. Perhaps stepping back from things a little bit, it's maybe easier to just think about the fact that if the valence band is curving down at C naught and the conduction band is curving up at 2 C naught, well, that means that the conduction band is a lot more curvy than the valence band. And remember, what I said is that since the curvature goes as 1 over the effective mass, the curvier it is, the lower the effective mass. And so just naturally thinking about it pictorially, because the conduction band is curving up twice as fast as the valence band is curving down, the effective mass of the electron is half as much as the whole effective mass. And a lot of you had, you tried to somehow do this more algebraically and got confused with E sub B and E sub C. So I want you to look at the solution and study it and make sure you understand how you actually calculate the effective mass from the curvature. Okay, going on to the final question, and that one was kind of like the last homework in the sense that I'm asking you to solve for now. I mean the difference here is that while it's a n-type semiconductor, I'm asking you to solve for P and the whole concentration. Now it starts with the same way to solve the problem, which is through charge neutrality. And basically charge neutrality is minus equals plus. Now in this case, there's no acceptors, so the only thing on the minus side is the n. On the plus side is the holes and the donors, which of course become positively charged when they give up their electron. Now I've shorthanded it, because I wrote that n, and of course, you were supposed to remember that np is ni squared always. So n, which is ni squared over p, is equal to p plus na, and solving, giving it in a quadratic form, and then using the quadratic formula, negative b plus square root of b squared minus 4ac over 2, and you get this for p. Now, that's the an answer. It's the right answer, and you of course got credit if you got to this point here. Then I wanted you to give me the approximate hole density, which was using the binomial approximation. So for Ni is much less than Nd, you rewrite what's in the square root here, taking the Nd out, and then it's times 1 plus 4 Ni squared over Nd squared, and the approximation for that, which is 1 plus x to the 1/2, is 1 plus 1/2 x, and so that 4 turns into a 2 there. So it becomes negative Nd plus Nd times that. The Nd's cancel, and you get this answer here, which was what I wanted you to do. Now, some of you tried to solve for an approximate solution for n first, and then use p as ni squared over n. That will lead to, you could get the right answer, that it will lead to some difficulties in making the approximation. So, I mean, this is the cleaner way to do the answer. Now, in the end of the day, if Nd is much greater than Ni, then N is approximately equal to Nd. So you could write P is equal to Ni squared over Nd that way. But I was very clear at the beginning. I wanted you to show all derivations. And so this is, for full credit, this was the solution I was looking for. Okay, so this was a test of the nanoelectronics YouTube system. I'm now going to see if I can upload it to YouTube, and then see if I can then give you access as private viewers of this video, and hopefully that'll go smoothly, and then we'll figure out how to do some more sophisticated lectures as we go forward. Thank you very much.